Hello guys, welcome to Organic Chemistry Exams Prep. This is Dr. Kulbhushan. Currently we are discussing the organometallic reagents. So far we have seen the preparation of organometallic reagents and the reactions and mechanisms of Gilman reagents. Now we are talking about Grignard reagents. So Grignard reagents general formula is RMgX, where this bond between this carbon and metal, it's very polar. It's got a very good ionic character. So because the magnesium is more electropositive, so it gets the partial positive charge, and the carbon gets a partial negative charge. Because the electronegativity of carbon is higher than the magnesium, therefore this shared pair of electrons is more towards the carbon. So now as we see that just like the Gilman reagents or alkyl lithium reagents, the Grignard reagents are also nucleophilic in nature. So the nucleophilic compounds or species would react with the electrophilic compounds or species. So we have seen the first reaction, which is nucleophilic addition on carbonyl carbons. So this is one of the most important reactions of the Grignard reagents. So our aldehydes, when reacting with Grignard reagents, would give us secondary alcohol, and the ketones would always give us tertiary alcohols. The primary alcohol is obtained only when a Grignard reagent is reacted with formaldehyde. Other than that, all aldehydes would convert to the secondary alcohols, and all ketones would convert to the tertiary alcohols when reacting with the Grignard reagents. So now the second type of reaction, this is also important, the nucleophilic substitution and subsequent addition on the esters and acyl halides. So this is a double addition of the Grignard reagent, and the product of this reaction is tertiary alcohols. So here we have seen the structure of an ester, but if this ethoxy group is Cl, then this would become an acid halide, acid chloride to be precise. And again, just like before, there are two steps to this reaction as well. First step is the addition of here it's methyl magnesium bromide, and second step is the acidic work. So if there were to be just addition of one Grignard reagent, then that would be the case. However, here there are four steps to get the product. So now let's see one by one the four steps. So our first step is the nucleophilic Grignard reagent attacks the electrophilic carbonyl group to form the tetrahedral intermediate. Now this first step is the addition of Grignard reagent. The second step is the substitution step, where the tetrahedral intermediate collapses and the leaving group leaves as ethoxide ion. So this step is the elimination. Now this elimination gives us the product, which is a ketone, and ketones are even more reactive than esters, which we will see in a minute. But let's finish the third step here. Third step is again the addition of Grignard reagent. So once again we get the tetrahedral intermediate, and this time because of acidic workup step, this alkoxide ion gets a proton to become tertiary alcohol product. So this is our fourth step, which is simply the acid-base reaction. So this base takes a proton to become neutral. So now to recap this mechanism, it has 4 steps. First step is the addition of the Grignard reagent to the electrophilic carbon. The second step is the elimination of leaving group. Third step is the addition of Grignard reagent, and fourth step is the acid-base reaction to neutralize the alkoxide ion formed as an intermediate in this reaction. So now this addition of Grignard reagent takes place twice. The reason for that is that the ketones, they are even more reactive than the esters. So towards the nucleophilic addition reactions, of course. So we can see the resonance structures here. So if you have a ketone, so we can show the resonance like that, because oxygen is more electronegative than the carbon. So this pi bond is more towards the oxygen. Therefore, the result of this resonance movement, or the movement of electrons, gives us this resonance structure, which is quite stable, and we can show how the resonance hybrid would look. So this carbon gets a partial positive charge and oxygen gets a partial negative charge. Now in case of esters, the first resonance is similar. So the oxygen gets a negative charge and the carbon gets a positive charge. So this is similar to what we saw in case of a ketone. But there is another possibility here, further resonance that is due to this oxygen here. So the lone pairs on the oxygen would make a pi bond here between the carbon and oxygen, and hence this oxygen gets a positive charge. And although this is not very stable, and this is a minor resonance structure because the oxygen is very electronegative and it doesn't like to have a positive charge. Oxygen, on the other hand, likes to have a negative charge. So now for the resonance hybrid, we can show that this oxygen gets a partial negative charge, the carbon gets a partial positive charge, and this partial double bond, this oxygen also gets a partial positive charge. So now we can see that there is only one resonance structure here, other than the, of course, starting structure. But in case of esters, there are more than one structures. So that's the reason that if you see this resonance hybrid, it clearly shows that the positive charge is not concentrated on the carbon only, just like it is in the case of ketones. So the positive charge is spread out throughout the molecule, especially a part of it is also on the oxygen of the ethoxy group in the ester. So that's the reason that it's not very electrophilic. So it's less electrophilic than the ketone. And that's the reason that ketones are even more reactive than the esters towards nucleophilic additions.